This is section 9.2, tangents. A tangent, geometrically speaking, so we're not talking about the tangent ratio that we saw last chapter, but in terms of lines and circles, a tangent is a line in the plane of a circle that intersects the circle in exactly one point, and that one point is called the point of tangency. So the line can only touch the circle in one point. I've got my purple circle O here, circle with center O, and I've got a green line labeled L, and they cross in one point, the point P, right here. P is the point of tangency. So we could write line L is tangent to circle O at P. What's true about the radius of that circle that is OP and the line L? Turns out those are always perpendicular, which you can kind of tell they're going to be. Looks like they make a right angle. But that's our first theorem today. If a line is tangent to a circle, then the line is perpendicular to the radius drawn to that point of tangency. Remember, we can draw an infinite number of radii within the circle. If we draw the specific one that goes from the center to the point of tangency, then that one is perpendicular to the tangent line. So that means that if line M is tangent to circle O at T, then OT, a radius, is perpendicular to line M. So I must have a right angle here if M is going to be tangent to the circle at T. That turns out to be really useful, and it helps us to understand this. This is a corollary to the previous theorem. That means it follows very easily. Tangents to a circle from the same point are congruent. So I've got two orange tangent lines here, both drawn from point P, so they come from the same point. Those two tangents are going to be congruent to the circle, are going to be congruent because they are both tangent to the circle. So PA is going to be congruent to PB. The reason has to do with, believe it or not, congruent triangles. If I just quickly sketch in the radius from O to A and the radius from O to B, those are equal because the radius is the same no matter which radii we draw. So OA equals OB, and we could draw in the segment PO, which is equal to itself by the reflexive property. Now we know we've got two right angles, so what we end up having is a little hypotenuse leg action there. So PA must be congruent to PB. Tangents to a circle from the same point are congruent. Our next theorem says if a line in the plane of a circle is perpendicular to a radius at its outer endpoint, so not at the center of the circle, then the line is tangent to the circle. So this is the converse of the first theorem we had. First theorem we had said that if a line was tangent to the circle, then it was perpendicular to the radius at that point of tangency. This theorem says if we've got a perpendicular line, a line perpendicular to the radius, then that line is tangent to the circle. So this theorem would say since line L is perpendicular to radius RQ, then L is tangent to circle Q at R. Since we've got a perpendicular line perpendicular to the radius, that line must be tangent to the circle, which means it can only touch the circle at R and nowhere else. Here are some examples of how we use these things. Let's say OT is tangent to circle R at the point O. We're going to complete each statement here. We end up with a triangle here. And we know this triangle is a right triangle because OT is tangent to the circle, so it's perpendicular to the radius from R to O. So if OR equals 6 and OT equals 8, we got 6, OT is 8, then what is RT? Well, it's a right triangle. All we have to use is the Pythagorean theorem. So for number 1, we'd say 6 squared plus 8 squared equals x squared. 6 squared is 36, 8 squared is 64, 36 plus 64 is 100. So x equals the square root of 100, which we all know is 10. So RT is 10. So because we have a perpendicular line, we've got a right triangle, and we can use all the stuff we have about right triangles. That is really useful. Number 2, let me erase my 6 and 8. If angle OTR is 45 degrees, OTR is 45, and OT is 4, what is RT? Well, if angle OTR is 45 degrees, we've got a 45, 45, 90 triangle. OT is 4, that's the leg. We got 1, 1, radical 2. OT is 4, RO, the other leg is 4, and the hypotenuse is 4, radical 2. So that is RT, 4, radical 2. So again, since we end up with a perpendicular line, we can make right triangles really easily and use the properties that we have of right triangles. Now a few definitions. We saw in the first section what it means for a polygon to be inscribed inside of a circle. We have an analogous definition of what it means for a circle to be inscribed in a polygon, and when that happens we say the polygon is circumscribed about the circle, like the circumference or circumnavigate. Circumscribed means to go around. So when each side of a polygon is tangent to a circle, the polygon is said to be circumscribed about the circle, and the circle is said to be inscribed in the polygon. The circle is inside, so it's inscribed. The polygon is outside, it's around, so it's circumscribed. I've drawn 2 examples here. I've got a triangle circumscribed about the circle, which means each side of the triangle is perpendicular to my circle. It's tangent to my circle. So if I draw the center of the circle, got a perpendicular line there, perpendicular line there, a perpendicular line there. If that's true, then each side of the triangle, all 3 sides, are tangent to my circle, so the triangle is circumscribed about the circle. Then I've got what turns out to be a rhombus over here that is tangent to my circle on all 4 sides. So the rhombus is circumscribed about the circle, and the circle is inscribed within the rhombus. Another definition: a line that is tangent to each of 2 coplanar circles is called a common tangent. So I've got 2 circles, both lie in the same plane. If they don't lie in the same plane, they're useless to talk about. So they lie in the same plane, and they happen not to be the same size here. And I've got a line that is tangent to both of them. When that happens, that line is called the common tangent. There are 2 ways that can look. The case on the left, you see the line sort of cuts across through the space between the two circles. When that happens, that's called an internal tangent, or a common internal tangent. The other case, the one on the right, is when the tangent line goes either above both circles or below both circles. It is not cutting across the space between them. That is called a common external tangent. You'll notice I've only drawn one common tangent for each of these. There's actually a second one. On the line on the right, I could start down and go up. In the picture on the right, I could go below the circles and have another line of tangency. It's not a very good line, but I just free drew it. And our last definition. Tangent circles are coplanar circles, they lie in the same plane, that are tangent to the same line at the same point. In other words, the two circles are tangent to each other. They both only touch each other in exactly one point. In the picture on the left, I've got two circles that do not share any interior points, and they're both tangent to that green line I drew. So these circles are called externally tangent. They do not share any common interior points. Circles on the right are called internally tangent. The circles themselves only touch in one point. Remember, a circle is just the border. We don't count the stuff inside. So the circles themselves only touch in one point, and they're both perpendicular to this pink line here. So they are tangent to each other. They are internally tangent because one lies entirely within the other. Here are your immediate practice problems. JT is tangent to circle O at the point T. Complete each statement. So what kind of a triangle do you have? Number 1, if OT equals 6 and JO equals 10, then JT equals what? Number 2, if JK equals 9 and KO equals 8, then JT equals what? Use the fact that KO and OT are both radii of the circle to help you on number 2. Please draw the picture, write the problems, and complete them. And that is the end of section 9.2.